Find the axial stress at failure when the confining stress is 150 kilopascals for a sand sample tested in the consolidated drain condition. In this problem, data has been provided from a triaxial shear test for a sand sample in the consolidated undrained condition. We begin by plotting the confining stress at failure from the undrained test, 70 kilopascals. Next, we compute the axial stress at failure to be the confining stress plus the deviator stress to get 170 kilopascals, and the point is added to the graph. A semicircle is drawn between these two stress values. Keep in mind, this is an undrained test, and the problem asks to find the major principal stress during the drained condition. So, the given stress values for the undrained test include the pore water pressure. The effective stress values can be computed by subtracting the pore water pressure from the total stress for both sigma 3, the confining stress, and sigma 1, the axial stress. However, we still need to compute the pore water pressure for the undrained soil sample. We do so by multiplying the density of water times the gravitational acceleration times the depth beneath the groundwater table. The pore water pressure at this depth is 50 kilopascals. Plugging in our pore water pressure and our total stress values, the effective confining and axial stress values are 20 kilopascals and 120 kilopascals, respectively. These points are plotted on the graph and connected by a semicircle. The pore water pressure of 50 kilopascals shifted the semicircle to the left on our plot. Now we have a semicircle for the undrained condition and for the drained condition. The problem asks for the drained condition when the confining stress is 150 kilopascals. Since sand is a coarse-grained, cohesionless soil, a point is plotted at the origin, and the rupture line is traced, tangent to the drained semicircle, and the angle of internal friction is identified. Since the cohesion is 0, the angle of internal friction can be computed by plugging in the appropriate stress values. The angle of internal friction is 45.58 degrees. The problem asks for the axial stress when the confining stress is 150 kilopascals. So 150 kilopascals is plotted on the graph, and the rupture line is extended outward. Next, a semicircle is drawn tangent to the rupture line and passing through 150 kilopascals. This graph is too small to see the value of the axial stress, but it can be solved mathematically by knowing the friction angle and confining stress, and by knowing that the cohesion is 0. The values are plugged in, and our axial stress computes to 900 kilopascals. Upon reviewing the possible solutions, the answer is C.